Welcome to the Plasma Physics course of TPFL. In the past module, we have started to introduce the rigorous definition of plasma. We have introduced the definition of the bilength, and now, today, with the present module, it's time to give a look at the last two definitions that we need, the one of plasma frequency and collision frequency. By these two definitions will allow us to draw the conclusion and draw the parameter space of plasmas. We start by giving the definition of plasma frequency. We consider a simple scenario. Let's consider a plasma that is a slab of electrons with number density n0. We will assume that the ions are a fixed background with the same density as the electrons. And then we will displace the electrons with respect to the ions by certain delta x. So what is the situation here? We have the ions and the electrons, and the electrons have been displaced with respect to the ions by certain delta x. What we want to evaluate is the frequency of the resulting oscillation. The electrons have been displaced, and therefore they will tend to be attracted back towards the ions, and this, as we will see, will cause an oscillatory motion of the electrons with respect to the background fixed ions. And what we want to evaluate is the frequency of this resulting oscillation. The first thing that we have to do is to evaluate the electric field. We do it by solving Gauss' law. Now, what is the charge that is present in our system? Well, we will have a region where charge is positive, then a region where the charge is above 0, and then a region where ρ will be negative. This will be the first region, second region, and third region. What we are mostly interested in is the electric field in region 2. Now, if E is equal to 0, at the left end here, then in region 2, by integrating the Gauss law, we will have that E is equal to n0 E delta x divided by epsilon 0. Have integrated the charge that is present in region 1 because of the displacement of the electrons towards region 3. We can now write the equation of motion for the electrons. As we know the electric field that they will be subject to, and that the acceleration of the electrons times the mass will be equal to the force, that is minus E times the electric field, and this will be equal to minus, with what we have just evaluated, minus n0 E square divided by epsilon 0 delta x. Which implies that the second derivative with respect of time of the displacement depends on a quantities that grows linearly with delta x. This is actually the equation of an oscillator, an oscillatory motion equation, with a frequency that is given by this term here. This is a frequency squared. It's an extremely important quantity in plasma physics that has a name. It's called the electron plasma frequency, and is typically denoted with omega PE. So a couple of observations. So the plasma frequency, which is, as we have just introduced here, is the square root of n0 e square epsilon 0 me, can be written as by dividing and multiplying by Te as the product of these two functions. And the first one, if you remember, is a quantity that we have just introduced, and is exactly equal to 1 over the Debye length, the electron Debye length, while the first one is what we are used to see as V thermal of the electrons. So there is a easy correlation between the plasma frequency and the Debye length that passes through the thermal velocity of the electrons. Second observation, how much is the plasma frequency? Well, in hertz, the frequency of the plasma oscillation can be written as 8980 square root of n0, where n0 has to be expressed in electrons over centimeters cube. Okay, before going to the details of collision frequency in plasma, let's try to remind us how collisional processes can be described. Let's imagine that we have a certain density of target particles. We will call it n target. And then an incoming particles, for example an electron, that enters, moves towards these target particles with a certain velocity v in. Now each part of this particle, as seen from the electron coming in, will have an area, collision area, that we will denote with sigma. This is also known as cross-section. Now the frequency of collisions will be proportional to the density of the target times the collisional area of each target particle, the cross-section, sigma, times the incoming velocity. The faster the electron goes through this target, the more particles it will effectively see in the unit of time. Therefore, the higher will be the collision frequency. Now, an electron moving throughout a plasma, what kind of collision can have? Well, it can have collision with neutrals. And the collision frequency associated with the collision with neutral will be given by the density of the target particle will be the neutral density times the incoming velocity, which can be approximated as the thermal electron velocity, times the cross-section. And well, for neutral collision, the cross-section can be very close to the atom, to Bohr size of the atom, where more precisely pi a0 over a squared, a0 is the Bohr's radius, is of the order of 10 to the minus 20 meters squared. But the electron can also do Coulomb collisions with other charged particles. And for example, an electron can impact against another electron while moving, and its trajectory can be deviated because of the Coulomb force. Now, when does this interaction, this deviation becomes important is when the Coulomb interaction energy is comparable to the kinetic energy. And how can we estimate the Coulomb interaction energy? Well, we can introduce the impact parameter. Basically, the distance of closest approach that we will denote with b. If the particles was continuing to unperturbed along its unperturbed trajectory, and therefore the Coulomb interaction energy will be given by E squared divided by 4 pi epsilon 0 b, and kinetic energy will be of the order of me v thermal E squared, from which we obtain that the deflection of the electrons impacting against another electrons will become important when this ratio is about 1, which means when the impact parameter is about E squared divided by 4 pi epsilon 0 me v thermal E squared. And this, for reasons that will become clear later, it's what we tend to call b pi over 2, b 90 degrees parameter. And now we have all the elements to estimate the collision frequency due to Coulomb collision. It's a very rough estimate. We will look more into details of the collision frequency, of Coulomb collision frequency later in the course. But basically, each particle, each electron can be associated with an area with radius b pi over 2. And the collision frequency will be given by the electron density times the incoming velocity of the particles, that can be assumed to be the thermal velocity, times the cross-section, that is pi b pi over 2 squared. And if we plug the numbers that we have just evaluated here, this will be equal to pi, what we have called n0, v thermal e to the power 4, (16 pi squared epsilon 0 squared me to the power 2 v thermal e to the 4th, which is also equal to n0 e to the 4th divided by 16 pi epsilon 0 square me to the power 2 v thermal e to cube. Now, in the rest of the present lecture, we will actually neglect the collisions with neutrals, and we will take into account only Coulomb collisions, which are the most interesting collisions you can look at in a plasma. It is now time to put everything together. The three definitions that we have just given, the bi-length, plasma frequency, collision frequency, to find out where we actually find the plasma in nature, in which parameter regime plasmas can be found. I briefly recall the definition that I have given. Plasmas are ionized gases, globally neutral, and that display collective effects. The two key concepts we had said was globally neutral and the collective effect. So let's review them in view of what we have just introduced. globally neutral, that means that the size of the plasma has to be much larger than the Debye length. This is in fact the Debye length, the scale length at which quasi-neutrality can be violated. And this will also tell us that the plasmas are, well, let's say not really neutral, but what we typically say are quasi-neutral on scale lengths that are larger or of the order of the Debye length. This is in fact the scale length at which any charge is screened and therefore whose effect is not felt farther away. The second concept is the one of collective effects. And this implies two things. On the one hand, we need to have that one-to-one interactions are weak. We want the plasma to interact through collective electric and magnetic fields that are generated collectively, as I was saying, and not that the interaction pass through collisions due to one-to-one particle interaction. And this, as we have seen, occurs when the number of particles in a Debye cube is much larger than 1. But it also implies one other thing, that the frequency, collective motion of the plasma is larger than the frequency of collisional processes. And using the definition that we have just introduced of the plasma frequency and collision frequency, we have that this is given by the plasma frequency times the collision frequency that we have just derived. And if we put these under the same square root, we find which can be written as introducing the Debye length as 16 pi, Debye length cube, this is actually the Debye length cube, times n0. And this is equal to 16 pi. This is the number that we have already seen many times today, and this has to be much bigger than 1. In other terms, both these conditions leads us to say that a plasma is a ionized gas for which Nd is much bigger than 1. We introduce also another parameter, G, that is defined as 1 over Nd, and this has to be much smaller than 1, and this is the so-called plasma parameter. So when do we have a plasma? We have a plasma when Nd is much bigger than 1. Let's see on a plot that represents temperature and density when this actually occurs. We can represent the temperature in Kelvin and the density in electrons times centimeters to the -3. And we will have, let me put some scale. The first line that I can draw is that represents when Nd is equal to 1. The second line I draw is for Nd equal to 10 to the 10. Therefore, plasma will lie above this part of the plane. They need to have Nd much bigger than 1. And in this part of the plane, we can find all the plasma we know in the universe. The solar corona, for example, will lies in this region. Ionosphere, plasmas in the ionosphere are located here in the phase space. Magnetospheric plasmas are here. Plasmas used for fusion application lie in this region. And then, for example, gas discharges, they are here. Well, these are the plasmas that we will actually consider throughout our course. Let me point out one thing that is important for the remainder of the course, is that in the range of parameters considered, we can ignore first relativistic effect, second quantum effect. Goal of the present lecture was to give a rigorous definition of a plasma. We have said that a plasma is ionized gas which is globally neutral and that displays collective effect. What does it mean? Well, to answer this question, we have introduced three definitions. The first one is the Debye length, plasma frequency, and collision frequency. And working around those, we have pointed out that a plasma is globally neutral when its size is larger than the Debye length on the one end, and on the other end, it displays collective effect when there are a number of particles in a Debye cube that is much larger than one. Under this condition, particles in ionized gas do not interact through one-to-one interaction, through one-to-one collisions, but rather through the electric and magnetic field that they have collectively generated. Based on this observation, we have drawn in a parameter space represented by density and temperature, where the ND number of particles in a Debye cube equal to one line falls. And we have made sure that the plasmas we know in nature falls in a region above this line. And this is actually the case. And we have localized in this parameter space where the plasmas that we will use and we will look throughout this course are